we're going to go ahead and get started. This is the Hardrock AMD considerations in room A. And so our first speaker is Brandon Holtzbauer Schwalzer. Close, sorry. Brandon received his PhD in environmental science from the University of Oklahoma in May of 2021 and immediately began working for Lincoln Energy. At Lincoln, Brandon focused on passive treatment and source control technologies while contributing to active mine water treatment designs and managing several projects. He currently lives in Lakewood, Colorado with his wife, 2 dogs, and a cat, and he spends most of his time working on the family's new house and exploring Colorado. Take it away.
Thank you for that introduction, and thank you all for attending the talk today. This discussion is going to differ slightly from the talks we had this morning, if any of you were in here, not only in scale, but also, we're looking more at bacteria, so, micro organisms here versus the macro large-scale efforts that we saw this morning. So our talk today, I'm actually presenting on behalf of my colleague, Jim Gusick. He's a mining engineer with Lincoln Engineering with over 40 years of experience in the mining sector, focusing a lot on passive treatment and source control technologies. So today we're revisiting bactericides, a 40-year-old and counting technology to help suppress the acid rock or acid mine drainage. So as all these talks normally do, we'll begin with a brief outline. I'll go over some background and some history about bactericides, discuss this ARD tetrahedron idea, give you some data on a research study and project that we completed. Careful, this is really sensitive. And then go over a path forward. So as a mining client, our clients, what steps would you have to take to implement this type of bactericide technology? So we're at a conference about abandoned mine lands, so it'd be prudent to start with the oxidation here of pyrite. It's AMD or ARD is that result of pyrite oxidation. This upper equation, we have the simple oxidation resulting in ferrous iron 2+, sulfate and a hydrogen ion driving that pH down. Then the second equation, we actually have ferrous iron being oxidized here and then serving as a catalyst to oxidize that pyrite. Now, because bacteria have been shown to kind of perpetuate this reaction, it increases the reaction kinetics almost 3 times or 1,000 times. We have to kill these bugs, kill the bacteria to help bring the kinetics back up here and suppress some of this proliferant formation of AMD. So looking at our acid rock tetrahedron, it's analogous to the fire triangle, if you would, where you have water, an oxidizer, pyrite, and some bad bacteria or a thiobacillus. So we need to not only kill this bad bacteria, but then replace it with a good heterotrophic bacteria so we don't just have a rebound of the acetothiobacillus. Wow, this is really sensitive. And then when you click it, cool. So if you've never heard of bactericides, a good place to start is this kind of starred referee publication here by Bob Kleinman. And then my co-author, Jim Gusick, actually contributed to this third reference here. Completed 14 years ago, and he's, we're hoping to keep this dynamic, somewhat unique, novel technology in the minds of individuals like yourselves and mining clients. So taking a bit of a step back, we've known bacteria have been involved in the oxidation of pyrite for about 70 years. Some of the early work focused on metal recovery like copper and gold. And then we learned that some common surfactants actually kill bacteria. And we'll discuss that here. I'll show you what killing bacteria looks like from an electron microscope. But the trouble with these bactericides is that they're so soluble. So a slow release pellet, as shown here in this image, was developed about 15 years ago. Unfortunately, it's no longer in production. So we've had to, kind of alter the application guidelines and develop some new techniques to apply these bactericides. But the probiotic approach actually gained favor about 20 years ago. And I'm telling you, it's not me. It's got a mind of its own. I'm just going to hold it right here. So essentially, we want to close the loop on this ARD suppression. And what we've seen from some of our studies, and we'll talk about this again, is that revegetation is actually key to the success of this. The humic and fulvic acids released by the vegetation actually acts as a bactericide in our favor, so you can not have to apply it into perpetuity. So another groundbreaking study here was this Kleinman and Erickson, 1983. If you're interested in bactericides or this type of technology, this is a great place to start. They showed that thiobacillus dramatically increased the rates of pyrite oxidation and developed some laboratory procedures that we'll discuss to determine what rates these solutions should be applied at. In the paper, they discussed two case studies. The first was sodium lauryl sulfate, one of the primary ingredients in like shampoo or detergent, the stuff that makes the bubbles, was applied to an 11-acre inactive coal refuse pile in southern West Virginia at a material cost of about $200 an acre. And acid production fell about 60%. I did nothing. I'm telling you. Acid production decreased about 60%, and we saw a 90% decrease in effluent iron concentrations. The second site, a very similar story, about 8 acres, same unit cost, and then we saw an acid production decrease of about 95% with a similar amount of iron concentration, 90-95%. And this temporary effect here, where they had to apply it 3 times a year, again, because this solution is so soluble, you need to keep it in the pore spaces of the rocks. This is where they use that slow release pellet. And unfortunately, like I said, it's no longer being manufactured, so we've had to come up with some alternatives. So I've kind of alluded to some of these. These are what are in our GeoPH pharmacy. Funny, it's better when it's up here and you actually see the word. But so some known bactericides, sodium lauryl sulfate, sodium laureth sulfate, those slow release pellets I've been alluding to, Promac, and then this alkyl benzene sulfonate. Laundry detergent is cheaper than just buying pure sodium lauryl sulfate. So how does it work? Well, first we need to consider how does any microbe survive in a low pH solution? Bacillus has evolved an oily membrane that keeps the ARD out, right? So we have a pH 2, 3, sometimes more, sometimes less, but inside it has remained relatively circumneutral. It does this and it uses its proton pumps to keep the protoplasm within the cell circumneutral. The shampoo actually destroys this barrier and allows the ARD to flood in, essentially killing the bug, stewing in its own juices. I'm telling you. Just more of that. So some other organic amendments, as I alluded to, we can use waste milk or dairy products. On small scale tests, we actually use like a powdered milk and make it up ourselves. That allows us to have any concentration of the solution. Typically, what I'm actually testing right now is a 1 to 100 dilution, just trying to make that milk. Did that just change by itself?
Next door, they're flipping a slide.
All right. Yeah, so waste milk, dairy products. I'm looking at 100% dilution. to try to extend that product, keep costs lower, things like that. We've also explored spent brewery grain. As most of you know, Colorado's got a lot of little microbrews, and we can get this material for relatively low cost. Again, just trying to use natural products that are considered waste to keep costs low and kind of close the circle on the carbon cycle effectively. And then again, kind of those organic acids that we're promoting through the development and continued proliferation of vegetation. So as promised, looking at a Phytocyllobacillus and how it reacts with those organic acids. I don't have my laser pointer anymore, but where those little black arrows are pointing, that's where the cell membrane was breached, and effectively the inside of the cell is leaking out into the environment. All right, so we do this at many scales, right? And we actually have each of these scales, the lab beaker test, kinetic cells, and field test plots actively ongoing at Lincoln Engineering right now. 2 weeks ago, I was out in Silverton installing a field test plot. I have some kinetic cells actively going at week 16. They're going to receive their amendment when I get back from the conference. And we just got some material from a mine in Nevada where I'll be beginning some beaker tests later this week. So what does this look like kind of on a full scale? Here we used the dilute milk to try and suppress the acid rock drainage. So framing the situation, we have an existing mine that was planning a multi-million ton expansion. The plan was to temporarily store the pyritic mine waste and then use it in about 20 years to sequentially backfill the pits, right? Filling in what they had already extracted. In the meanwhile, they would actually need to increase the capacity of the active plant, the lime dosing plant that they had on site. So they considered several options. They looked at co-disposal, but unfortunately, because of cyanide regulations, that technology was avoided. Obviously, like I said, they looked at the expansion of their lime dosing facility, and then kind of a third, everything works better in threes, is this application of bactericides. So essentially, the question becomes, can we use a bactericide to suppress ARD formation in a host rock that has 8% pyrite? Okay, well, that's the question. How do we answer that? Well, get some material. Just as I said, we have the material sent to our lab in Golden, Colorado. We'll do some acid-base accounting, maybe some mineralogical work, depending on what data the client has available. Then we'll expose it to some beaker testing. At beaker testing, look at that. That's what the beaker testing looks like. And that's to essentially see if there's any fatal effects, right? Like if we apply 1 to 10 dilution of milk, does it curd up and essentially no water can flow through it? Things like that is kind of what we're looking for. Or if we add like a sodium lauryl sulfate, does that change the pH and cause the export of different metals? Things like that. It's a very high level kind of a, not best guess because there is science involved, but it's a modified U.S. Bureau of Mines screening test. So from there, we put in kinetic cells and kind of repeat the process. Have a control, different combinations or concentrations of the bactericide, and then run the analytical data afterwards to look at the effectiveness. So as you've already seen, some of our material flowing through some Buchner funnels. In the top picture, we actually like to use solo cups. Although that's not very scientific, it's cheap. And it allows us to look at the inside of the cell while some of these reactions are ongoing. So if we do have that curdling, we'll see it in the cell and can, rather than try to guess as to why no water's flowing through it, we have, we can point, take a picture and say, hey, use a higher dilution. Some examples of our kinetic cells. So this is, pictures of things we actually did with a client's material. So this is, like our kinetic cell setup, 5-gallon buckets with an inert, river rock underneath. that actually protects a drainage layer, so you can add water, flows through, and then you get your effluent after a certain interaction time. And I won't go too into that until here. So we did 8 different tests. It might be a little difficult to see, but essentially we had unamended host rock, our controls. Then we looked at adding sodium lauryl sulfate, both buffered with lime and non-buffered with lime. And then our milk is highlighted as number 5 and 8. The difference between those is the establishment of vegetation. Number 8 had vegetation, number 5 did not. And that'll become important as we look at some data here. So this is all of our data. On the y-axis, we have effluent pH. The x is weeks with the 8 different kinetic cells. And I've highlighted number 8, 5, and the control. Again, our control, nothing was added to it, the do nothing alternative. 5 was the milk with buffering, and the top kind of gives you a little key. And then number 8 was a duplicate of 5, so same milk concentration with the lime buffer, but we actually established vegetation on it. So we can see, effluent pH with the vegetation dramatically increased relative to the control. We're looking at effluent pHs of around 6, where our control in almost every other cell is down below 3. After about 14 weeks, all of our cells started to mimic the control. So again, those applications probably were flushed out of the KCTs if they weren't continuously applied. Again, because this stuff is so soluble, you need to have either a cover or continuously apply. Somebody earlier this morning mentioned the COVID hiatus. We did have one of those as well from about week 21 through 28 there. So that's why we have the data gap. Looking at our iron concentrations, yes, those units are correct in milligrams per liter on the y-axis. So we're talking about 12 grams per liter of iron in the effluent of our number 6, which is that lime buffered with sodium lauryl sulfate. So I added another one just to show you that we can push these things the wrong way, which is why you need to do this testing and not just, there's no magic bullet for any mine site. You have to go through, do your homework, and demonstrate that this will indeed work. I think the data kind of speaks for itself. Number 5 and 8 being the milk amended, and number 8 again having the vegetation. So we're seeing that humic acid produced by the vegetation act as a bactericide, killing some of those acetylthiobacillus, and then the milk provides that carbon component for the heterotroph. So we're having a population shift. So zooming in, 5 and 8, it's kind of hard to see because we're at 2,000 milligrams per liter. So we extracted them out a little bit so you can see some of the variability here. And then our number 8 cell, pre-COVID hiatus was down near detection limits. So coming from, 12 grams per liter down to detection by applying milk in a vegetated cover, it's better than treating into perpetuity, I would say. And then our sulfate changes. So, that reaction I presented, sulfate is a byproduct of that. We're decreasing the reaction kinetics, thus the formation and generation of sulfate by destroying some iron oxidizing bacteria. So that's a nice little segue there. We did some most probable numbers looking for acetylthiobacillus. And we can see again that our number 8 had less than 3 colony-forming units per milliliter compared to about the 4,000 colony-forming units that we see in some of the other kinetic cells. So why? I think, if this data didn't speak for itself, why would you consider bactericides? We know what works. It'll be different at each site. Again, there is no magic bullet for ARD prevention. Our goal is to avoid the ARD treatment now and forever into the future. Some of those active treatment technologies, sure, membrane processes are great, but it's energy intensive, person hour intensive, and you have to treat into perpetuity. And while you're developing your closure plan, thinking about, the minimal maintenance required for these systems, periodic, infrequent inspections, they're not no maintenance, they're low maintenance. You can, use some existing or old technologies, drip irrigation to apply your milk. We demonstrated, buffering of our reagents, that lime buffered sodium lauryl sulfate. And then with, recent advances in vegetation technology, the use of organics, soil stabilization, compiling all of these things together really is a blueprint for success. So again, this is kind of the track that Lincoln takes and that I would, suggest to you. Do your homework, figure out the acid-base accounting, how much pyrite you have, conduct the lab, the bench, the pilot scale studies. It is time intensive, it does cost money, but the benefit in the long term is invaluable. And then obviously look at the economics, right? We want to assess the feasibility of the bactericide application, versus the perpetual ARD treatment. So hope I convinced you to give us a call, but thank you for your time, and I look forward to any questions you may have.